Okay, so far things have been in this transportation business quick and dirty. And yes, what do I mean by quick and dirty? And this means that I want to criticize a little bit this solution 9.4 we just had. So what was quick and dirty there? Well, obviously the fact that the solution was ad hoc. Ad hoc, Latin meaning for this purpose only. And yes, if you have to solve one problem, ad hoc solutions are good because they are quick to do. But then suppose that you want to solve these transportation type problems, many of them, then it's kind of tedious and extremely boring and error prone, really, to always do an ad hoc solution. So always build the objective function and the technology matrix and constraints from the problem data. Instead, it would be nice to have a function. Let's call it trans solver that does this for us. And indeed, this is precisely what we have next. So we have a function. I call it trans solver. You can download it from here. So it's a function m file transsolver.m, and that takes in the transportation problem data, supplies, demands, and cost matrix, and returns the optimal schedule and its associated cost. And indeed, you should download it from here, and after that it is at your disposal. So if you want to solve the following exercises, or the previous ones actually, so if you really want to solve these exercises with this, you are actually welcome to do so. If you do it that, then you miss the joy of finding out the ad hoc solution of for yourselves. But if you don't find that too joyful, then you are invited to use this function. So here is actually what this function looks like. So we have an extremely long introduction block here. This is something that if you type help trans solver, this is what is printed out. There I also kind of played out a little artistically with the sum signs. Yeah, I was bored. All right. So here is short explanation, very short input ST and C, supply vector, demand vector, and cost matrix, and output schedule and cost. So this will be the optimal schedule and associate minimal transportation cost. And this C also GLPK, so obviously this is more or less a wrapper to GLPK. So we will transform the problem data, supply, demand, cost into objective technology bounds, and then solve it with GLPK. So here is then a very short explanation how this function works. So first, this is a function m file, not a script m file, meaning that the first thing that does something, so these commands do nothing, is a keyword function. So now Octave will understand that this is a function m file. So we have output parameters is the optimal schedule, and then the associated cost, schedule cost, then name of the function, same, that is the same as the file, so that's trans solver. Note the two S's there, and SD and C, the input parameters. So what then happens is the next three lines are just shorthand notation, if you like. So now I use slightly different notation that I used in the notes. Sorry for that. This was not intended, but maybe again it's good for you to see that symbols can have different names. So M1 will be the number of sources, M2 will be the number of destinations, and N, which is the M1 times M2, is the number of routes, which is also the number of decision variables. Okay. let me omit what happened here for a while. Of course, that's the most difficult part. Let's leave the difficult part for the last. So here the technology matrix is somehow built. And now we have the technology matrix. What then happens? Then I set the sense of the bounds. So we have upper bounds for supplies and lower bounds for demands. And this is done with a construct that we have seen before. So first I have the C type I start, is the constraint type I start it to be empty string, there's nothing there yet. And then for loop that goes from 1 to M1, so this for loop is looped the number of sources time M1, and then I append the C type with U. So this will build the C type with U, as many as I need for all the sources, and after that I append the destinations. So now I have a for loop that going from 1 to M2, so M2 is the number of destinations. So I have the C type, which at this point has some U's there, and I append L after the U as many times I need, so that's as many destinations I have. Finally, I need to do a similar thing for the var type, so the variables. So how many variables I have? I have, well, M1 times M2, which I have denoted here by n. I have n variables, so I need to have a string of C's, so C n times, and yes, this happens here. So the V type variable type start with an empty string, and then in the loop that goes around n times, there is a C appended there. Then I solve by using GLPK. So this we saw in the ad hoc solution, the quick and dirty solution before. So schedule cost will be GLPK. Okay, so the C will be the cost matrix transposed and unfolded. Then A, so the B will be the S and D. Next one, LB, UP, they are very often to us just the empty matrices. And then C type, V type, as they were. And again, the sense would be +1 because the minimization, that's default. I don't have to give it, so I don't give it. And note the important, I have semicolons everywhere, so this is a function. I don't want it to output anything. I just want it to or print out anything. Of course, I want it to output only the output variables. In this case, they would be the schedule and cost. And so, final touch here is the schedule is now a vector, so the schedule corresponds to the big X we had before. So I have to reshape it. So this is actually the correct way of reshaping it. Took some experimenting from me to understand which way they go. I didn't try to understand it. I just tried out and then realized, okay, this is the way it should go. So I take the schedule, and the first parameter is M2, and then M1, and everything went fine except that the rows and columns were the wrong way around. So then I just transpose it. Yes, this is how it goes. Okay, the final part here, which is of course the extremely complicated part, is what happens here. So what happens here is the general form of what we had basically here and here. So I'm building this matrix in a general sense. And what happens, so you should compare it with this. So I start with, okay, there is a certain amount of ones, but most of them are zeros. So what happens, I figure out first what are the correct dimensions. So the dimensions will be that there are m plus n, m1 plus m2 rows in this A, because the rows are the constraints, and I have m1 supply constraints and m2 demand constraints. So I have M1 plus M2 constraints. So that's the number of constraints I have. That's the number of rows of M. How about the columns then? So the columns are the decision variables. And how many decision variables I have? So the decision variables were related to the routes, and how many routes there were? Well, M1 times M2, which is what I denoted by N here. So this will be N. And now this is a trick, so I have actually an I going from 1 to M1. So it's the number of sources that I do, and then I actually fill in the supply side and the demand side at the same times. So here we use this kind of what we had exercises about block matrix formulations, and this is where that's needed, or where that is very convenient. So this is the supply side. This one's from 1 to M2. This means that, again, let's go back here, the quick and dirty. Here, this is filled in the first round of the for loop, and the second round in the for loop, this is filled in. If there would be a third round in the for loop, there will be ones filled in here, and so on. And at the same time, when this is filled in for the supply constraints, I fill in this identity matrix here for the demand side. And in the next round of the for loop, when this is filled in, this is filled in. And if there are more rounds in the for loop, meaning we have more sources or destinations, then again more and more identity matrices are filled in on the right hand side there. On the right, sorry. So this is what happens here. And yes, I know this is complicated. This is very complicated. And in order for you to understand it, you should play around. You should just test this by GNU Octave console. I will not go into more the details of this. This is the part that since now you have this function, you can use it. So you don't have to, at this point, okay, to be completely honest, you don't have to know how this function works. You can just use it. But I mean, if you want to learn more than just the bare minimum, I think it's a good idea for you to understand what's going on here. Also, it is a rather typical things you have to do in programming to have some kind of non-trivial for loops when something fancy happens. All right, but now let's go to the solution 9.7. This is the spice must flow with highliners. So this is the solution of what we already had. You can also download this from this link. And there is, well, this is now very simple, really, because the whole point here is to show you how convenient this transsolver function is. So how do we solve the problem? So here is again just a title block saying what we are doing, and then there is a data, and note that the data is now the supply, demand, and cost. This is all I have to give. That's the whole point. And then I solve with transsolver, so x cost will be transsolver STC. Note the missing semicolon, so it will print it out. And then if you run this on the console, so you just type highliner once you had this highliner.m and transsolver.m in your current directory, you will get the same solution and the same schedule and same cost, of course. All right, so that was all about the primal transportation problem. So let me now call it again primal because of what happens in the next section. And yes, this transsolver program indeed I encourage you to download it, and in the exercises, if you wish, you can use that to solve the exercises related to transportation problems. That's all for now. See you in next videos.